All right, we are here to do some stat solver work today. Last time I got this naive transformation done, so the naive transform takes in a general Boolean formula and turns it into the CNF, the conjunctive normal form uh, that is equivalent for that. I do at some point need to do the other transform, which is which has better properties of not exploding the size of the formula too much. This one we talked about last time, how it when you do the transform that way, you can potentially grow the formula exponentially larger. But we have a test case right now of a Sudoku problem, and it turns out that this particular problem does not, like the way I've expressed the constraints here, does not actually lead to an explosion of the size when we do the naive transformation. So the naive transformation is good enough to turn this into just a nice basic problem. If we turn off the solver and run it, you can see what the CNF looks like. Or wait, this isn't the CNF. This is the Boolean formula. Let's see if here it is. Okay, so underneath we have the CNF version. Let me just make these labels a little nicer. So if I do that, then we get CNF. Yeah, cool. So you can see it just generated the CNF, and the size of the CNF is, let's see, so the SAT formula, 49, almost 50,000 lines, and we come down here, and it's like 60,000. So yeah, it has not grown large at all. In fact, it looks like it's not anywhere near as big, but the reason it's so many more lines in the SAT formula is because here we put a separate variable on each line, and here we managed to put like all of the, like this would turn into one line down here, these 4 lines. So the 50,000 lines here turned into about 10,000 lines here, and point is it did not explode the size, which could have happened. Now, the next problem I want to deal with is, while this is a good CNF formula, if I run my stat solver on this, what it should do is it should provide for me, it should eventually conclude that you can in fact create a Sudoku board, right? It's possible to fill a Sudoku board in such a way that all the rules are followed. And right now I don't have any constraints on the board. Like I don't have any built-in numbers that are fixed. So it's just an empty Sudoku board, and I'm just asking the stat solver, hey, is there some way to make at least one valid Sudoku board that is filled with all of the numbers, right? And it's not working. So when I run this, it'll take a few minutes, and then it'll say that it couldn't find a solution, and it very clearly gets into some bad states along the way. So what I want to do first is excuse me. I just choked on my own throat for a second there. It was while I was talking, man, all of a sudden lost control of my ability to move my throat the right way. Okay. The thing I want to do is I want to look through the current state of the solver. So that's this here, this function, and just read it out to myself to remind myself how the CDCL solver that I've written actually functions, and then maybe figure out what to do from there. But I want to download into my head the structure of the CDCL solver. All right, so we have this thing called CDCL begin, which is giving us the CDCL. So the whole solver sort of keeps its ongoing state and variables inside this structure here, which is just local to the solve function. And let's see, so skipping the logging, the first step is it comes into propagate. So this is all in a big loop, but the first step is to propagate. So propagate means if there are any variables that we can deduce perfectly, like if there are any variables that we can be sure what their value has to be, we go ahead and assign those. And the way that's happening, let's get very concrete here. The way that's happening is we do this eval clause function. Now eval clause is being run on every clause in the whole formula. So it then scans all the literals in the clause and evaluates them one at a time. So the way it does that is it goes, we have this array of assignments. For each assignment, for each variable, there is an assignment value, and then we use that to figure out, okay, so yeah, we're using 1 to encode true and -1 to encode false. That's fine for now. That's a low level detail I'd probably like to change later, but it's fine. And this is checking if it's a negated version of the literal, then flip the value that's stored in the assignment. Okay. If we see anything that evaluates out to true, then the whole clause is good, and so we say total value 1. If we find something with a value of 0 in there, then we increment the total value to 0. We can't be done yet because there might be a 1 later, so we're kind of escalating, right? The total value is equal to the maximum truthiness. We have false, undetermined, and true, and so there's like 3 levels of truthiness in this assignment system. And when you see an undetermined variable in the clause, you increment this free literal count. This is how many of them are free. And by free, we mean undetermined. Maybe unassigned. And so if we get to the end and the clause has an indeterminate value, and we have exactly 1 unassigned literal, then that 1 unassigned literal has to be true. Because we have to make each clause true. Then we have isolated unassigned literal. And then there's our result. Okay. So if we have an isolated unassigned literal, then right here we do the work of assigning it. And then it restarts the whole propagation from the beginning with that new information. So this is a very clunky way to do propagation, but it does work. So that's good. Now, if we got a conflict, what is a conflict? A conflict clause happens here if we check a clause and find out that all of the variables in that clause are false. Or if all the literals evaluate to false, then the whole clause evaluates to false. So we call that a conflict clause. So if we have one of those, we stop propagation and we deal with the conflict. And then we go into CDCL learn. And this is quite different from the mini sat. This is the one I read from the first sat solver I read. And so this is a little bit, I think it works, but I think it's a little funky compared to what I saw in mini sat. So the learn resolutions, literal count, literals. What's the literal count? I plus equals 1, literal plus equals 1, variable. Gets the variable assignment. We read the assignment. So we're looking at initially we're looking at a clause and we're looping over that clause. If as we loop over that clause we find a variable with a constraining clause and a guess number that is equal to the current guess number of the solver. So it's from the current propagation tree, and it's not the root, it's not a guess. Then we do this resolve function between the clause we're looking at and the constraining clause. And okay, this is making more sense to me now that I've spent enough time understanding SAT that it's making sense to me why this works better than it used to. So the two clauses come in. This is where we do the sort on the literals. And we create a new clause where we are deduplicating variables. So the variable we're looking at here it was originally in the clause we were looping over, and then we found that that variable had a constraining clause. Those will never be the same clause for reasons I'll explain later when we do a picture, but that makes sense. So we take those two clauses, we were doing this merge and removing all of the duplicate variables. Mm-hmm. And then we've got a new clause. And then we set that new clause that we just generated to the accumulator clause. And that can come back as a 0 if we end up eliminating all of the literals along the way. So if we eliminate all the literals along the way, we end up with an empty clause. And if we have an empty clause, then we need to then there's no solution to the problem in it. And that's, again, a little hard to explain now, but that makes perfect sense to me at this point. So if we go here, we give up and result equals, where does result get set up? Okay, got it. So what's happening here is if we have a 0, then we end up returning 0 from this, right? If we try to learn a clause and we end up with an empty clause, we just end up returning a 0. If we succeed at learning a clause, what'll happen is we'll get through one of these loops and we won't find any variables that are at the current guess level and that have no and that have a constraining clause, right? So we'll have probably one variable that'll be left to be the guess variable from the root of the guess tree, but all the other variables that were there will have been systematically eliminated by this and reduced down to a single final clause. So the learn should be correct, I think. I think that the learn is correct. On that, at least on that pass, it looks good. So if learned clause does not equal 0 after that, then that means we in fact were able to resolve the conflict. We can learn a clause and keep making progress. So the conflict is resolved. We attach this clause into the formula. Then we have to determine a backtrack point. The backtrack point is determined by looking through the learned clause. The learned clause has a bunch of this is wrong, I think. I think this part is wrong. I remember feeling suspicious about this part before, and I believe the correct thing to do here is to say we're going to unroll the current guess number. Well, let's take a look at one other thing. What does my backtrack function do? So backtrack is coming up later. It takes in a guess number. Okay, so this is going to undo everything So let me think. When we go to do a backtrack, what we're going to have is we have all these different guess numbers. One of them is the most recent. At least one variable always has the most recent guess number. The others maybe range from small to large, and we want to take the largest one. We don't want to backtrack to the first guess that we made in this process. We want to backtrack to the spot where we made this guess. And we want to keep this one in place. So when I say say if this is guess number 0, 1, 2, 3, and 4, I'm not going to take the 4. I'm going to scan and take the max of the rest. I'm going to find a 3. And so I'm going to say once I've figured out that I want to undo to 3, I want to undo everything up to... I want to undo everything after 3, but I want to keep 3, right? So this would mean if I'm backtracking in such a way that if I put a 0 into this, then it wouldn't ever be able to undo the stuff that happened during 0, which makes sense. The 0 layer is like unchangeable. The 0 layer is where we don't actually ever, if we can't make things, or how do I want to put this? The decisions made at the 0 level have to be there. There's if we needed to backtrack them, that would be the same thing as saying there's no solution. So if I put a 0 into this, that might as well mean get me back to the point where the number of guesses I've made is 0, and all I have is the stuff that's forced. Right? So then, for all the assignments that are above the guess number, we unset them. And then we set this like that. And now, if that's the plan, then what we're doing over here is we're saying... let's see. Let's grab this. So that's not allowed. That'll start like that. And this will be the max, not the min. I don't want to backtrack everything every time. I just want to backtrack to the first guess where there was clearly a deduction I could make based on what I've learned that I didn't make. Okay. Now, what I want to do, I think I get the rest of this. This is a little bit more pretty simple stuff. So this is where we make a guess. This just goes into the heuristic for guessing, applies the assignment, and then goes up there. So this is all right. It's not exactly what I want. I want to show you a picture now. So let me rearrange things a little bit so that I can draw. Let's pull up Milton. And this guy here, wipe down the screen a little bit. All this dust, okay. All right. So let's call this the fat sat notes. Okay. There's the top there. All right, so what I want to show you is the solver, CDCL solver flow that I want to build. So I've ingested the current state of things. Now I'm going to draw from a picture how I would like it to be working. Like, so I'm taking the first thing I did, loaded that stuff into my brain, setting aside and forgetting it for now. And next I'm going to imagine the structure of a solver sort of from first principles on the blackboard here. And then what I'll do is I will compare the two once I've got both pictures in my head, right? So the CDCL solver flow goes like this. When you begin, the first state is propagation. And during propagation, essentially 3 different things can happen. During propagation, you can find out that you have a conflict. And if that happens, this is like where we start. Right. If we have a conflict on our first propagation, that just takes us straight to unsatisfiable. Okay? Now, another thing that can happen during propagation is that you get, I don't know what you'd call it exactly. You could get everything is satisfied, so we'll just call that the SAT result. And that takes you to you're done. So this would be like if you had a really trivial problem where it was possible to logically deduce the solution without having to make any guesses. You know, some variable sits in a clause by itself, so it gets set, and that forces you to set another variable, and that forces you to set another variable, and eventually it all just kind of solves itself, right? It's possible. And then another possibility out of propagate is that we're undetermined, right? So we get like undetermined status. And when we finish propagating and it's undetermined, then the next thing we have to do is make a guess. So when we make a guess, then what happens, there's only, let me try that again. I don't like the look of this arrow. Undetermined. Then you make a guess. Okay. From a guess, there's only one result. Like, you don't fail to make a guess. There's not different outcomes. So after you make a guess, you go back into propagation. But I don't want to go into that propagation because that propagation is just for the initial pass, right? Like that's just the initial time. There's a separate way we wire propagation's results up differently after the first time. So we go to propagate again, but we propagate differently. Or rather, we propagate the same way, but we handle the results of propagation a little differently from now on. So after we make our guess, we do more propagation. When propagation finds SAT, it'll still go back up here to SAT. So, right, SAT still goes this way. But unsat is going to come over here. So this is what do we call this? A conflict. Conflict is now going to flow over to clause learn, or yeah, what do we call this? Like learn. And backtrack. Right? So when we hit a conflict, let me do that better. Learn and backtrack. Okay. Now, learn can fail, in which case we get unsat. Or we can succeed, in which case we go back to guessing. Or actually, we go back to propagating. So if we learn a new clause and we backtrack, then we take what we've learned and we begin propagating again. Now, propagation here might be a special, unique kind of propagation, but I'm not sure. It might also just want to be general, good old-fashioned propagation, or it might be propagation with like a slightly unique primer. So the flow into propagate might do something unique here. The reason I say that is because we just learned a clause. I think what we probably want to do is backtrack to the point where we can take that learned clause and deduce something from it right away. So go back to the point where this learned clause would have caused a deduction earlier in the process. Go to that point, make the deduction, and continue making more deductions if possible. So that's if we succeed at learning a clause. Now, the last thing that can happen during propagate is that you get an undetermined, and in that case, we just go back and make more guesses. So if we are not in conflict and we don't have a satisfying assignment, then we go back and we make more guesses. So this is the solver flow that I want. Okay, we start here, we do an initial propagate. That can lead into an unsat state, into a sat state. These are, by the way, the final states. These are where the algorithm ends. If we get an undetermined result from propagate, we flow into guess. Guess always flows into this propagate, which does the same internal logic as this, but it wires out in slightly different ways. If this finds a conflict, it goes over to learn and backtrack, which then comes to here. And if this sat or undetermined go in the same direction, okay? So what I'd like to do next is sketch out the skeleton of a new CDCL solver. I'm just gonna write from scratch. So I could try to tweak with the one I've got, but there are so many things I'm going to change that I feel like I'd be wasting my time. I've spent enough time learning about sat solvers now that I feel more comfortable just trying to write from the ground up. So let's tear out. Yeah, let's just tear out all of the CDCL solver functions we have. Here's the old one that we had that I wrote off stream a few weeks back. Let's write a new one. And so fatsat CDCL backtrack, where's the one I want? CDCL guess. Okay. And then if we come up here, the CDCL struct. Yep. I'm going to wipe that out too, and there we go. All right, now the fatsat solution, that seems fine, but we're gonna need a new solver here. Okay, so I don't actually have I'm not gonna actually have a finished solver all in one go, but I wanna reconstruct this flow now. So there's propagate, that can be conflict sat or undetermined. So one way I could handle that is to say propagate result, and then after we've done the propagate part, I'm going to comment that out so I don't actually have to implement a thing called propagate. Then if propagate result, why don't we call this fatsat? So what would we call this? Path, maybe? So if the path we see is the conflict path, then I mean, what I'm really tempted to do here, if I show you what I'm really thinking, is to just, like, say, this is going to be like this. So we can switch on the path value here. Look at this. So conflict goes to unsat. CDCL path satisfied goes to sat. Case fatsat CDCL path undetermined goes to guess. Right, and then in here we have to write a propagate logic. But that's only if we're in this version. In this version, it would be a little different, right? So the difference would be that conflict needs to go like, if CDCL guess number equals 0, go to unsat, else go to learn. Okay. So that way, when we flow into propagate, the guess number should be 0 if we're here. And it should be non-zero if we're here. And it's actually possible now that if we backtrack, that another result is we backtrack to 0, and that would be the equivalent to going to here. But that actually makes sense. I hadn't even thought of that when I was writing down my flow. But that's the right thing to do. There is a way to go from the learn path to here by succeeding at learning a clause and backtrack to 0. Right? If the result is succeed and backtrack to 0, we would end up here. So it's a succeed, but it'll set the guess number to 0 so that when we come here and propagate, we're propagating on 0. And when that happens, what it means is we're propagating on something that has to turn out true for the whole thing to even be satisfiable. If we are on level 0, then that means we learned something that was basically a proof that a thing had to be a certain way. And if that leads to conflict, then the whole thing is stuck. It's not just stuck because of an earlier guess. Okay. call this V1 because we probably make adjustments to this over time. All right. So that's how propagate will work. Or that's how propagate fits into the flow. We're going to need a CDCL solver with a guess number. Why did we have a CDCL begin? It does have to do a little bit of stuff. Okay, so we'll probably just assume the same thing is coming again in this case, like that. Set up our scratch. Okay. Okay, right? So there's the idea. And then, let's see, propagate. Let's set up the flow for guess. Guess is simple. It doesn't do anything complicated. It always flows back to propagate. And we've already handled that propagate. So then learn. Yeah. So that, and then learn can go to, let's try and see here, instead of naming it fail and succeed, well, conflict, satisfied. I mean, I could call it fail and succeed. The problem is I don't actually need these. So I'd like to be able to reuse the codes between these, because if I make these like all match, we'll just call it fail, succeed, and undetermined. So we got 0, 1, and 2. So these should make for nice jump tables, hopefully. And this, when it fails, goes to unsat. When it succeeds, it goes to propagate, right? And propagate in this picture looks like 2 separate nodes, but actually it's one node here. We put an extra branch in the flow paths to distinguish between these, and there's only one type of thing, succeed. The backtrack to 0 will happen as part of the logic of learn. Okay, so that's everything except for sat and unsat, right? So if we say go to sat, then let's see, how did we do this before? I'm going to take the solution pointer and let it live up here, with the idea that we'll go this, or rather like this. So if we go to sat, what we do is we say solution equals now before we were doing result equals this, and then yeah. So I give it an arena, and I need to give it, I'll just give it the CDCL solver, and it'll read the solution off of that. And then we'll have another one which is just called unsat, which doesn't need that. And those can look like this. So in this case, you just do that. In this case, you go satisfiable equals 1. Variable count equals variable count. Values equals values. Grab a couple of these and fill those up. So the CDCL does want to contain those assignments. I'm going to rename some things here though to make it a little tighter. Okay. And sorry, that needs to go here along with the variable count. We want to set up the enum. Fail, succeed, undetermined. Failed, succeeded, undetermined. Yes, and so then the solution in this case just comes from this function, and we go to end, unsat, 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 go to end, cool. All right. So that's the basic sketch of the thing. We've got those are actually implemented. So it's just these things where we've got to do a little work. Okay. Now, what I want to think about next is looking again at the flow. What is some information that needs to get carried along these wires? Well, when we do propagate, nothing needs to get carried because propagate doesn't actually return anything. All it does is modify the assignment, which is carried along by the CDCL, which we already have. If we make a guess, so right now if we make a guess, we don't need to do anything because the way that we've been thinking about propagating is that propagation is just a thing you can apply at any time with no context. You just start going and you apply it to all the clauses. we might want to change that. We might want to say that sometimes you propagate without any starting point, but sometimes you propagate by having like an accelerator, like the watches from the minisat thing. So I might need to slow down and think about that. There might need to be two different types of propagate after all. One that flows from a guess number. Although we could just look at the CDCL guess number to figure out where to start the propagate logic. That only kind of works because, right, so this is a primed propagate. It can be primed from a guess, or it can be primed from this, right? And this is unprimed propagate. Hey, Wizard of Datums, welcome. And then, let's see. When we learn, this definitely wants to carry some information. That's the primed information there. So there's a couple spots here where I might need to carry information around, but it doesn't seem like any of it carries by literally needing to pass a value. It more carries it by writing it into the CDCL solver state. The conflict does need to pass something, now that I think about it. So when we propagate, if we get a conflict, it's going to pass a clause to this. So I've got this flow. This is nice. Let's talk a little bit about what structure I want to try to build. So I could build the fastest possible thing that I know how to do, which is using the pair of watches that I learned from Minisat, that technique. Or I could do the really slow one that's just propagate by going over all the clauses over and over again. Just to get something up and running. Let's talk about what would happen during the guess. We would want to have some heuristic here that would make useful guesses. And I think some of my ideas about how to make useful guesses are interesting, but I want to actually start with something so simple, and I don't want to have to get bogged down in how to do this. So what's a way to do that? The simplest way to make a guess would be to just pick one at random. Let's just fill that in here. So variable count. Yeah. Let's say the CDCL solver wants a PRNG on it. Let's see. Make from C. There we go. So that sets up my pseudo-random number generator. And then I should be able to just go next bounded on that whenever I want to make a guess. So I'll go like this. Well, I need to pick an unassigned variable still. So even if I did this, it would be a little bit more work. I could just take the first unassigned variable every time. It'd be kind of dumb, but that'll get us started. Wrong file. Assignments, right, so we're going to do All right, so we look at the assignment value, and if that's a 0, we're just going to always guess true. Guess variable I equals I break. So there we go. There's a heuristic optimized for being something I can write in a tiny amount of code and without having to make a complicated data structure that sits alongside everything else. So there's our heuristic optimized for not being hard to write. Now, I take that and I do make a guess. So making a guess entails did I have before? I don't know if I had one for this. Yeah, make a guess. Oh, but that's okay. Let's go read what that was doing. What does the guess function do? Allocate counterbanks, determine guess from counterbanks, pick most common variable, pick guess. Okay, so then it would return the guess. And I guess you would call assign. Okay. And assign would do take the assignment there, guess number when formed, constraining clause, right, fill the assignment. Okay, got it. So we're just talking about like we go guess number goes up by 1 before we place the guess. We can do a couple of asserts. Guess variable I needs to be less than CDCL variable count. The guess variable needs to be unassigned. And then we want to fill that with a value. A guess number. And the deduction clause is null for a guess, because we didn't make a deduction, it's a guess. So that's how we make our guess. Okay. In case I do want a random number generator later, there it is. Guess value. Okay. So that's how we make our guesses. Let's carry on in a similar fashion with each step here. So how do we do our propagate? We do, yeah, let's just do this in the simplest way I can imagine. So we're going to do what we did before, basically. Which is we have this loop over the clauses. Right, okay. We're going to structure it like this. Formula, we go over the clauses. Now it's evaluating the clause using this eval function. I'm going to just short circuit that, pull it right in. So we have a total value equals -1. This the same way. We do this the same way, although I'm shortening the name here. And then if we get to the end, instead of filling our result and then reading out from the result, we'll just do this stuff here. So we got to the end here. If the total value is -1 at the end, then we have path equals failed, break out of this loop, and we want to set the conflict clause to the clause we just looked at, and the conflict clause will live up here. Conflict clause, so that we can pass it from propagate to there, to wherever that links to, right? If that links to unsat, doesn't matter. If it links to learn, we need to see the conflict clause. If the total value is 0 and the unassigned count is 1, then we can make a deduction. And what we do to make a deduction is we go, okay, give me the variable of the unassigned, compute the value that the unassigned needs to have in order to, based on this deduction, right? Then we want to make the assignment. And this is where maybe we want to pull this out. So we have fatsat CDCL assign. Here's the CDCL. variable of value deduction clause comes from the clause we're looking at. This one is guess variable, guess value, no clause. Either way, we want one of these hanging out up here. So the rule then is like this. Assign value guess number clause. Lay that like that maybe. All right. So CDCL guess number, guess value 0, CDCL variable value clause. Okay. So if we are making a deduction, we do that, and then what we do is we set the clause pointer back to the beginning of the loop. So this is just the dumbest possible propagation where we are trying to get through an entire loop over all the clauses without making any conflict discoveries or deduction discoveries. If we want, what we could do is we could go satisfied clause count equals 0, and whenever we start the loop, we'll set that to 0, and go like this, right? So if we got to the end and the satisfied clause count is equal to the formula clause count, then we can set this to succeeded, this path here. And we already have, here's where we find a fail. So that's doesn't need to be the default. Here's where we find a succeed. But if we get this far and satisfied clause count is less than clause count, we're either in the failed case or in the undetermined case. So we don't want to override failed. So what we want to do here is say at the very beginning, we set the path to the undetermined value. Right? So that's the default. And then if we get through this and we manage to not find any conflicts, and we don't make any deductions, and we don't find that they're all satisfied, then there are some clauses that are neither satisfied nor in conflict, and they're not ready to make deductions, so they are too unresolved. There's like several clauses with two variables that are unset, two or more variables that are unset, I should say. And in that case, we're in the undetermined case where we need to go make a guess. So that's the default, and if we happen to find that they're all satisfied, then we're done. If we happen to find that there's at least one conflict, then we go to the the appropriate path for that as the special cases. Okay? So that's propagation. All we have left is learn. Okay, how does learn work in this? So in order to learn, what it does is it gets a conflict clause. The conflict clause is a list of literals, and it wants to so we know a few things. One, whatever the conflict clause is, it can't be the case that the only literal in there from the current guess number is a guess itself, right? So let me draw you this picture. Whoops. Whoops. No. What did we do? Okay. So what happens here, right? Let me start from here. What happens here is we have these guesses, right? So a guess is like this. Here's a guess, and each guess contains within it some assignment. Right? A guess contains some assignment. And then what can happen is some deduction gets made. So a deduction is like this. It's like an arrow, and then another assignment right here, right? Guess, deduction, right? Now the deductions are based on guesses, so they're not fully get deductions in the sense that they're 100% logically proven, but they're proven given that guess. If we assume that guess is correct, then these other things can be deduced from it. Now, as that happens, that arrow there is kind of interesting. That arrow isn't just an assignment. It isn't just nothing. Like the dots here are assignments, there is actually a clause of literals living here. So we could say like X, Y, Z, right? Maybe this is not X, not Z, and Y. And if this is determining that Y is true, right, so there's another assignment. This here is a clause. And the clause was in the state that, if X, in this guess here, we made this literal false. Let's say earlier Z was already set to true, so this literal was false. So we were then in the case where we could make a deduction. Well, a deduction is driven by a specific clause. Each clause can make one deduction. It's the one for the variable that was unassigned. And each deduction has one clause attached to it. So we have this pattern here of assignments are living on the points, the guesses and the deductions, and clauses live on the arrows. And so what we can do if I clean up this picture and simplify this, I'm going to put less labels on it now. We make a guess, we make a deduction, right? And we might make several deductions off of the first guess. So we start forming this tree. We might even have situations where our deductions lead to deductions. But another thing we can spot is that these clauses have, these arrows are clauses, right? So the yellow arrows are clauses. They have relationships out to certain variables, which in turn have relationships to certain assignments. So if we made a deduction here, it must be the case that we couldn't make that deduction sooner, or we would have done it. We make the deductions as soon as possible. So when we make a deduction, we can go, oh, this assignment here must have impacted that clause, which means this clause has a literal that went false because of this assignment, right? Similarly, this assignment must refer to a literal that shows up in this clause. And this right here, this assignment must have a relationship to this clause here. So each of these deductions, the deduction point is a literal that lives inside this clause, but the assignment before it also lives inside the clause, right? So we have two assignments or two variables that both relate to the clause that live in between them, right? So each of these edges, these yellow edges, is a clause, and the two endpoints are two of the variables living in that clause. It's also possible that there's a relationship between this and this, right? So even though this didn't directly cause this deduction, it was this that caused the deduction, this helped us push in this direction because this assignment here could relate to this clause as well. Suup asks, what version of 4Coder are you using? I'm using the default version of 4Coder. Let's see, version number information for you. I think this is the most up-to-date version. It's been a long time since I double-checked, but I think all my machines are on the most recent official version of 4Coder before the community fork started. I don't have any of the community fork or custom stuff. Cool. So this is what a deduction tree looks like, or let's call it a deduction tree. At its root, it has one guess, and then all these deductions come out. And then while we're running the algorithm, the CDCL solver, right, we can make multiple of these guess trees, which can start to look, or these deduction trees. I guess I'm going back and forth on what to call them still. Right, and they can start to look like this. And those red arrows, if we keep drawing those in, they still exist here, and here, and here. They might also exist like this. But they can also exist in another way, which is things from here. So it's possible that this deduction factors into this clause, and that this deduction factors into this clause, and that this deduction factors into this clause, right? Like, that's all possible too. So they can't go backwards. The red arrows, it can never be the case that a deduction or guess in the future was a part of a deduction in the past, because deductions have to flow from things which are assigned. They can't flow from things which are unassigned, right? And as assignments are being made, they force information to flow forward but not backward, right? They force deductions to flow forward but not backward. So when we get to finally a conflict, what that means is, instead of having, let's say we're here and we find a clause that is forced by this and this and this, right? Just making up random arrows here. So those three variables, those three assignments all relate to this clause here. So this X is a clause now. Right? Up until now, all the clauses in the picture were these yellow arrows. And these red squiggly arrows represented the assignments that were contributing to constraining a clause so that a deduction could be made. Now we have a clause that ended up false. It ended up completely in conflict. All of its literals are false. So that means if we have a complete picture here, this assignment, and this assignment all come together to make this clause fail to be satisfied. So then the question is, what do we do with that? This is where learning begins. We take the conflict clause and we say, okay, we had this all along, but we failed to look ahead and see that these guesses were going to lead to this conflict. So what we want to do is we want to roll back from this conflict clause and build a new clause out of it that would have allowed us to see ahead more easily. This would be a clause that would have prevented this particular guess, this particular chain of guesses from forming in this way to lead to the conflict. Now, there's a few things we can say about a conflict clause. At least one of its literals must be inside the current guess, the current deduction tree. Otherwise, we would have noticed it was in conflict sooner. Just like with deductions, we notice conflicts as soon as possible. So if we're noticing it as soon as possible, it's not going to be the case that the current guess tree was irrelevant and we just happened to find a conflict clause. No, if we're finding a conflict clause, it's because we just set something that relates to that clause. Now, another thing we can say is that if only one variable in this entire tree relates to that, that's possible, because it's possible that this deduction here forced this variable to go true, but if we had gone a little farther, we would have found a different clause that would have forced it to go false, right? These two, this clause here, this one, and this clause here, remember those are both pictures for a clause, want the same literal to go two different ways. And in that sort of a case, it could be that this is the only variable. Well, let me think. I mean, if this is there's another thing we can say. It can never be a guess, right? It can never be that the single variable, let's say it's possible that there's a single variable in the current guess or deduction tree that relates to the conflict clause. If it's a single variable in that tree, it can't be the guess. Because if it's the guess, then that would mean that this clause was already primed and ready for a deduction. It was in the critical state where a deduction could be made. And the deduction would have gone the opposite direction of this guess, right? It would have been relating to, it would be relating to the same variable as the guess and with the opposite value, right? And therefore, we would have made the deduction in the tree beforehand, in the previous deduction tree, right? We would have already made a deduction, and this guess would not have been one we could make. So if we're making a guess, we're making a guess because there was no way to make a deduction, which means whatever variable we make a guess about cannot cause a conflict right away, right? Guesses are always safe directly. It's just through these in deductions that conflicts can arise. So what we know is that this does not contain only the guess. It might contain the guess plus something else, but it can't contain only the guess. Now, as a final note, it has to actually contain at least two things, and now we're ready to see why. The reason it needs to contain at least two variables from the current deduction tree is that if it only contained one from this deduction tree, then that means all of its other literals were constrained back in this deduction tree or in previous deduction trees, right? If it's possible to bring it into conflict in this deduction tree, that means it was not critical at the begin when this guess was made, because right here there were no critical clauses. So this clause went from undetermined to critical to conflict all within this guess tree. In order to make those two changes, 2 variables in this deduction tree must have been relevant. Okay? So, now, what we can say is this clause here could be simplified in a couple of different ways. The easiest thing we could do, the very easiest thing we could do is we could say, okay, this guess here was bad. Let's learn a new clause that would prevent that. And the way we would do that is we would look at all the previous guesses and say, okay, if all of these are true, then this must not happen, right? Once you've made these particular guesses, this guess is illegal, right? And so that clause would be, you just ignore the initial clause, or the conflict clause, and you build a new clause that says, one of these things has to be false. One of the guesses you've made had to be false. And so when all of these guesses were already made, that would have forced this guess to turn out different. And that would make something kind of like progress, but we can do better. And the way we can do better is by looking at some of these is by pushing forward towards something closer to the conflict clause. And the reason we want to do this, we want to get to the point where we would have had this guess be ruled out earlier, but we don't necessarily want to have to grab all of the guess variables here. So another way we could do it is we could start walking backwards through the red arrows. We could go, okay, well, let's see, that's a part of this guess tree, that's a part of this guess tree. Oh, this one here touches this guess tree, which touches this clause, okay, and then we go back, and so we just grab the guesses that are relevant, right? So that would at least narrow it down. And that way we're not saying that we've learned, what we've learned becomes more specific. More narrow clauses are more constraining. They are more useful as learned clauses, right? So that would be a little better. But we could go even farther. Like in this case, we could say, all right, if we look at what's happened here, if this variable becomes true, right, or if this assignment occurs, if this particular assignment has occurred, then we can see that leads to this conflict, right? This assignment and this assignment together are enough to create the conflict, right? These two assignments, if we have them, well, that sets this to false, and all of the rest of these deductions here, well, that's not quite true. So what I said was almost true, but not quite. This deduction, this assignment, and this assignment don't quite force this, because while this did force these two assignments, in this case, if we look at why that worked, it was also because of these two things, right? So if we have this and this and this and this, then we have a problem, right? But we don't have a clause that says that, right? If we can see that if I have these assignments here, this one, this one, this one, and this one, then I have a conflict, because once I have those three, that's enough to lead to all of these deductions, which then leads to this conflict. So these assignments imply a conflict, therefore these assignments themselves are a conflict. So it cannot be the case, we have to have a new clause that's like, not this, or not this, or not this, or not this, right? That's the clause we could learn. We could also clean it up a little more, right, if we wanted to. We could look at this and go like, hey, look, this thing here, and this thing here, and this thing here all followed from this. So, like, maybe in this case, the correct thing to learn, the most efficient thing to learn would be just, hey, don't put this together with this. But these would both be true statements, right? I could say learn the clause that this and this don't go together, or I could say learn the clause that this, 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 and this don't go together. What's the advantage to one or the other? Well, the first one is smaller. That's nice. The other one is nice in that it relates these variables. So if I were to unroll this guess later, right? If later on I unrolled this guess, but then I made this guess and this guess, then I would already be pretty close to the conflict happening again. Not 100% of the way there, but like right now, then I could see like if I only learned about this, the relationship between these two assignments, then I don't notice what happens if I unroll this and put these things in, right? But that's like a trade-off. It can go either way. As long as we learn a clause that is necessary, so it shouldn't be a clause that changes the problem, and it should be one that contains this variable, right? It should be one that would have prevented this guess. Then we've made some kind of progress, and the rest of it is like fine-tuning of which particular kinds of clauses we prefer. Do we prefer ones that are as proximal as possible? Do we prefer ones that are as narrow as possible? Do we prefer to remove redundancy as much as possible? Or do we prefer to learn more quickly and not do the extra compute that goes into like removing the redundancy? There's a lot of questions there that are more subtle, but the main one for when we go to learn is we need to learn the clause that involves rolling back to this assignment. And so the way we do that, the way we're going to do that is we're going to take a look at this conflict clause, and we're going to look at each of its literals, which its literals are these red arrows, right? These red arrows are the relationship between this assignment and this clause. And the way an assignment relates to a clause is that that clause contains a literal, which is negated or made false by this assignment, right? So we're going to look backwards through these, and we're going to go, okay, hey, look, this one here, this one's interesting because it's in a different guess tree. So keep an eye on that one. This one, okay, that one's in the current guess tree. So what we would then do is go, okay, if that's in the current guess tree, take a look at this one here. We get this, and we get, oh, sorry, that's not true. When we look at this one, we find this, and this are the relevant ones. So keep rolling it back. We find we're interested in that one. That one, not so much. That one, not so much, but we'll keep rolling it back. Looking at this one, oh, hey, we already are going to look at that. That's great. So looking now at this one, that relates to this. Oh, we've already marked that one, and it relates to this. Oh, hey, that's the root. That's perfect. Then we look at, let's see, which ones have we, I should check these off. So I've looked at this one, or rather, the things I want to check off are, I've looked at this, I've looked at this, I've looked at this. Then I came in here, I looked at this, I looked at this, I looked at this. I came in here, and I looked at this right here. I looked at this. So those are the ones going into that yellow arrow. Now let's see, I need to go to this one. And, so this and this haven't been marked yet. When I look at this, I want to keep that one. And that one's already been marked, so good. And then finally, looks like we've looked at all of them, right? We've looked at all of the circled spots. Starting from this, we looked at this, 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 and this. And so now these square ones that we found by that process are the ones we want to put together into a new clause. And then what we want to do is we want to figure out how far to backtrack. And the answer is we ignore this literal, which is in the learned clause, in order to figure out the backtracking. Let's say this. Right, so those are the assignments for the learned clause. And then for the backtrack, what we're going to do is we're going to say, okay, looking at each of the squares, we're going to ignore this one. and we're going to say take the max level, so most recent, we want the most recent guess / deduction tree represented in the learned clause, right? And so the most recent one represented in the learned clause, ignoring the most recent guess. Right? And so that means, in this case, we would backtrack to here, and then we resume propagation with new clause right there. Resume propagation here with the new clause. And the reason we want to do that is because we know that the new clause would have led to a new deduction right here. This, all of this information here has been preserved. The only thing we've unrolled is this, and we are now in a state where if we had gotten here before with the clause we just learned, we would have deduced to set this variable the opposite way. And so we want to see what happens if we do that, right? That's the idea of the learn and backtrack. Okay, so now to get a little more concrete, how do we want to learn this? Let's talk that through one more time looking at the picture. We have a clause, we scan its literals. For each literal that is outside of the current guess tree, we just store it into a growing list of the result. If it's in the current guess deduction tree, then we're going to revisit the thing we found. We're going to say, oh, we found another one, revisit this one. And we don't add it to the list. Then we do that for all of the literals in the current clause. And then we go back through those assignments and that we put into the queue to handle later, and we look at their reason clauses. If they have a reason clause, right? So when we get to that, it's a little different. But if it has a reason clause, we scan that reason clause's literals. And we do the same thing. If it's outside the current guess tree, we store it into our literal. If it's inside the current guess tree, we store it into the queue. With one exception, if it's in the current guess deduction tree and it's the guess itself, it's in the deduction, then we stick that, we ignore it, we don't put it in the queue because it doesn't have a clause for us to iterate. And when we're done, we take that guess and we put it into the clause as well. We put that into the learned clause. Then we might have gotten some duplicates along the way. So there's a couple ways we could avoid that. We could keep a bitmap of all the variables and say if we've seen the same variable twice, don't go down that path again. That seems like a fine solution to me. So let's see. Finally, we scan it one more time to figure out what guess. Yeah, this, I wouldn't even have to do that. Okay, this seems like not that big a deal. All right, rearranging now. Hopefully this was a useful and accurate description of how this is going to work. So what we're going to need is an array on the Scratch arena. We probably want we want a local temp for this kind of thing. And then we want one of these for each variable. We then want to keep a local clause, CNF clause. Yeah, we want to keep like a resolve clause, which will start off as the conflict clause. I'm thinking something through for a moment. Okay, I think this is good. So the one thing we don't have that we need in terms of data structure is here, is we need a queue of the clauses to get back to. You know, each time we see one of these, we want to queue up its reason clause, and we need some kind of way to grow out the learned clause dynamically. So we need a dynamically growing like chain of literals or something to flatten out after we're done gathering it, something like that. So let's build those real quick. Okay. So we should be able to do that. I'll make a free list as well in case that gets that complicated. And then instead of a resolve clause like that, what we could do is stick right there, Q free, Q first, Q last, like this. Or we could go like this. Grab this. First, last, free, ref, Q, conflict clause, push that onto the queue, and then do a loop that says if the queue first is not 0, grab the clause this. We pop one clause off the queue, and then we will handle it here. So let's go implement these helpers. CDCL begin assign solutions. Okay, here's where we'll put the queue. Fatsat CDCL clause queue push. Queue CNF clause. There's our clause, and here is our popper for the queue. All right, so first things first, we want to allocate a ref. So we get that off the free list if possible. If that works, then we just pop it off the free list. Otherwise, we push an array onto the arena for that. That gives us our clause. And then we want to make sure to push that onto the actual queue. Queue first, queue last, ref, okay? So that puts the clause onto the queue via clause reference. Here, we want to go, all right, if the queue is not empty, then we just take the clause off the first one. We're going to pop it off the queue. Let's see, I think we want to do something like clause ref, grab the ref pointer first to return, and that way we can push it onto the free list. Right? So I need to grab that out so that when I return, what I'm returning is just the clause, and then the clause reference is the node that goes on the free list so that I can reuse it. That's a CNF clause. CNF clause. No need for an arena on that one. No need for an arena on that one. CNF clause, oh, CDCL clause ref, thank you. Return the result, and there we go. Okay. So we've got our queue of CDCL clauses, or CNF clauses coming through. for each one of those, we are going to do a loop. What do we do on the loop? I don't like that. So we want to look at each literal, and then we have to do a couple of steps. So we want to get the variable from the literal. Each of these should be assigned. Initially, because we're on a conflict clause, they should all be assigned false, or they should all be assigned so that they evaluate to false in the current clause. But after that, we'll start chasing down those deduction clauses, and those will lead to us discovering that there are true or that some of them will be true, right? There will be a true one somewhere in there. So it doesn't matter how it evaluates, but they will all be assigned. Now, the point is to look at the assignment now. Right, we want to grab the assignment by looking at the assignment for that particular variable. And what we're looking at for in this assignment is, what's the guess number? Does it have a deduction clause, right? That's the information we're interested in. If the guess number if the assignment guess number is equal to CDCL guess number and the assignment has a deduction clause, then we're going to push the deduction clause onto the queue for processing. Oh, before we do all that, one of the things we want to do is we only want to deal with the variable if we haven't actually seen it yet. So if not seen variable, then go ahead and do this, right? So if we have not seen the variable, let's set the variable as seen. We only want to deal with each variable once. And then there's two things we could do with it. One is we could discover that it contains a deduction clause that we want to dig into further to keep digging back, looking for the root of the current guess deduction tree. We know they're all part of the same tree because they all have the same guess number. But the one that doesn't have a deduction clause, that's the guess we're actually interested in. That's the assignment we're interested in keeping in the final learned clause. Otherwise, if the guess number is less than the current guess number, then we want to put this into the output chain of like the loose new clause. So we'll call the CDCL clause loose. that'll look like this. Literal. Okay. So that's good. Except I do need to figure out how I'm gonna find the root guess assignment somewhere. And add that first. So there are ways I could do this that would be preferable, and that would include something like building the data structure that keeps track of my guesses as I go as a stack, and then I could look at the top of that stack. That would be my most recent guess. I think for now, what I'll do is I'll say this. We're going to do if the deduction clause does not equal 0, then we are going to chase that deduction clause down. If it does equal 0, then we do the add lit on that literal. Okay? And maybe as a side bonus, we will also remember that particular literal, because I do have another idea for what I want to do with that. So this will be the hold on. I think this is the wrong literal to learn. Let me think. So the other literals I want to learn. Okay, this is interesting. So this is an assignment, which means it's a variable and a value, right, together, right? An assignment is when I take a variable and I give it a value of true or false. So this is a variable value together. Then this thing here, right, is the constraint propagating from this assignment onto a clause. So like, let's pick an easy one to see here. This arrow means that this particular assignment led to the variable related to this assignment appears in this clause, and the value in this assignment causes the variable in this clause to evaluate to false, right? So if this is assigned false here, and this literal appears over here, then it's coming out false. If this is assigned true, right, then the negation of that variable appears as a literal right here, and so it evaluates to false. One way or the other, when these red arrows appear, that means they're appearing, propagating the enforcing constraint on this clause, pushing this clause towards being critical so that it can make a deduction. Which means that not only does the variable here appear here, but the valence of the variable is known as well. And the valence in this clause is the opposite of the valence in this assignment, essentially, right? Now, when we're deciding what literals to put into the learned clause, we're not just interested in which variables. We want to get the valences right on the learned clause. And so if we're saying, hey, if you assign this way, the same variable with opposite of valence appears in this clause, right? Now we're iterating the clause looking at its literal. So we're not looking at the assignments that we did make, right? We're looking at the assignments, or we're looking at the literals that appeared in the clause. And so we're saying, hey, this clause here said this should not be true and you made it true, or that it should be true and you made it false, right? And we want to learn the opposite of what we did here. Well, the opposite of what we did here is what's stored in the clause. So learning the literal from the clause works. That's not quite true in this case, right? If we find the root of the guess tree, well, is this right? No, I think it's still appearing as a red arrow. So the way it appears here is the opposite of the way we guessed it, which is how we want to learn it. So I think it's fine. I think we want to just grab literals from these clauses where these clauses got constrained. The only places where the clause will have a literal that's evaluating to true is, so the one spot where there's a relationship between a literal and a clause in this picture that I didn't draw is that these literals relate to their clauses backwards as well. Deductions relate to the clause behind them. But instead of having this opposite relationship, they have the equality relationship. They have the same valence, right? So what that means is when I look at this clause, for instance, it's going to have this literal here, this literal here, and this literal here all appear. The one which appears in the same form as in one of those literals evaluates to true, and it's this one, right? And that one's already been marked as seen, so we're not going to scan that clause and do anything with it, right? When I mark a variable as seen here, and then I take its deduction clause, then when I scan its deduction clause, I shouldn't end up touching that variable again. So I won't learn anything, like I won't accidentally do anything with that variable, and I won't get caught in a loop either. The guesses don't have a positive relationship to any of the reason clauses, right? They are only negatively correlated to the reason clauses that come after them, but they don't have a reason clause, so they don't have one where they go, hey, I have the same valence as this one here. And they also shouldn't appear in any of the reason clauses that come before in previous trees, because reason clauses should be ones that are fully assigned, and this was a guess, which means it was not assigned yet, so it can't appear in previous deduction guess trees. Which means I think these are the correct valences for the literals to learn in both cases, I think. I don't think I have a way to encode. I think that's as close as I can get to encoding the idea of unassigned, so hopefully that's a good idea. That'll be a low-level thing to change later. But here's the critical literal. The critical literal is the one whose variable we assigned at the root of the current guess deduction tree, right? It is the one that we guessed, and the valence on this literal is going to be opposite to the one we assigned, making it the way we would like to learn it, right? So if we set this to true and it led to a conflict, then what we want to do is learn a clause that would encourage us to make it false. And the way we do that is by putting the false literal into the clause, and then we pair it up with these things, which are the other most proximal reasons for why this thing had to be the opposite value, right? And these things, we put in the opposite of how we assigned them so that they all evaluate to false in the learned clause, and the only free thing would be this, so it'll get assigned the opposite way. And that's just, we're learning it that way initially. Then it just sits in the system from then on and can, if we roll back farther, it can direct deductions in other directions too, which is the even better part, that it sort of represents permanent progress. But we want to know that there. So once we're done, well, let's go build the loose clause real quick, right? There's our Q. Here's our loose clause. The loose clause clause loose clause. Loose literal. This is a very, very loose structure. We'll probably want to optimize it. So we can grab like, you know, like something like, what would it be if that's 4 bytes? Something like this, I think, right? And then, you know, possibly even just go like, you know what, screw caches. This doesn't have anything to do with caches. Just make it big so we don't ever actually need multiple of these in almost any case, right? But for now, we'll just go with 1. Makes it easier to get it started. And then we go first, last, and so this doesn't really need to look like this, I don't think. Instead, it can just go like this. And so Q push, clause Q push, clause Q pop, function void, clause add literal. That onto the arena. And then we need a way to bake that down. We want to loop over the loose literals. inlet equals inlet literal, da 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 da, and then you fill in the clause. And there we go. Don't like that anymore. I want that out. Okay. Assignment. What am I missing? First and last are both fat, sat, loose literals. Loose literal, loose literal. What are we talking about here? Ah, this one. Yeah, yeah. Cool. Okay. Clause add lit, but we're not done. I still need to use that big function. So here's what happens. When we get to the end, it's possible that the learned clause is empty, right? Wait, how could that ever be possible? Could that be possible? That was the structure of the CDCL I learned from before. There has to be a way for learning and backtracking to fail, because that's the only way to get back to unsat after the first propagate. Unless the point is that you learn something that causes you to backtrack to level 0 and then you find a conflict. Let me go check minisat again, because I'm realizing now that I don't see any way for this to be empty. Because even if there are none of these, you would always have the fact that this guess shows up in the literal, or in the clause. So if nothing else, you could always learn that that is false. And if that's true, you don't have an empty clause, which means you don't have this path. And so the only way to fail completely is if you backtrack to 0, run propagation, and find a conflict. Let me go check. No, minisat. Oh man. So that's the solve function. We have propagate. I actually want to check the propagate function again here, because I think there's something funny about that that I haven't thought through, which is how it runs differently on the first pass versus later passes. Got to think about that. But Okay, if we have a conflict, analyze, that's what they call it. Analyze. Okay. Yeah, it doesn't look like their concept of analysis has a failure mode. Right, so here's analyze. I don't see anything in here about returning information about. So let's about if it succeeded or not. Maybe here, cancel until backtrack level. If size equals 1, you just queue that right away. Yeah, no, it doesn't look like they're doing that. Okay, that satisfies me. Okay, so let's modify this. This is a misunderstanding that I had from the first CDCL solver that I don't need to keep. So there is no failing here. Learning always works. And the only question is which propagate you go back to, right? Yeah, that seemed good to me. So really at this point, this picture is too complicated. Let's redraw it. Okay, so we start here. First step, we propagate. If that leads to an undetermined state, we make a guess. That after that guess, we keep on propagating. If that leads to the discovery that we have completely satisfied the
the formula, then we go to the final satisfied state. Whoops. All of a sudden, can't remember how to draw those. Okay. Now, if it comes back with a conflict, at stage 0, that's what takes us to the unsat state. And otherwise, we have a conflict where we learn and backtrack. And then that takes us back to the propagate. Okay? So we have a loop that goes, okay, do propagate. If we have an undetermined state, guess and propagate. If we find a conflict on non-zero, we learn and backtrack and propagate. And then it has two other exits, which are just sat and conflict and unsat, right? So this part, it can be the same. Guess can be the same. Learn always goes back to propagate. Then sat and unsat. Okay. So path is no longer a thing we have to deal with everywhere. It's just a thing we have to deal with here. Good. Okay, now we grab our CNF clause. And for now, what we do with our CNF clause is we push clause. We push onto the formula the learned clause, and there you go. It's a little bit more simple than what we maybe want. We probably want to keep them separate and learn how to I do have a question. Does the formula itself carry an arena? No. Okay, so there we go. New clause. Let's call that the loose clause, maybe. Okay. So we bake that and learn it. The other step is we want to figure out the backtrack level. Which starts off at 0. And every time we look at a literal in this loop that is not from the current guess number, the backtrack number becomes the max of its current level and the assignment guess number. So we learn the clause, then we're going to backtrack to let's go look at how backtrack got implemented and just do that right here. Okay. Now to backtrack, what we're going to do is we're going to loop over all of the assignments. And if that assignment was guessed after the current backtrack number, then we zero out that assignment, and when we're done, the CDCL guess number becomes the backtrack number. And finally, we want to make a deduction. So that's just an assignment at the current level. This is going to be the deduction variable and deduction value, and the learned clause is the reason clause. So we have a deduction literal. So to make a deduction variable from that, we can just use the usual way of getting a variable from a literal. There's our deduction variable. I'll just name that variable and value like this. And then for the value, we just have to go, okay, did the is negated, literal is negated. We look at, we want to set that to true unless the deduction literal was the negated version, and then we want to set it to false, right? Cool. Okay, now if I don't have any mistakes in there, that should be a new CDCL solver. I don't want to run this on Sudoku because I feel like I won't be able to tell if it's failing very easily. So let's simplify the test case for now. Let's just say, trying to think of a very simple, satisfiable problem. Okay, so here's a simple one. We're going to have nine total variables here. 0, 1, 2, 3, 4, 5, and 6, 7, 8, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, got it. Those are my 9 variables, and my rule will be an implementation of XOR across the 3 bits. So XOR is like this. For I, U32I is less than 3. Give me a root here. So so we want to have one that's like if they're both true, and another one that's like if they're both false. And then we want one is that says if this or this, right? So they're both true or they're both false. And then what we want to do is we want to say, all right, if this is true, then this should be false. So in order for that to work, what we want is I think I want to put the not on this side, not, and that's at con, nor is the not of or. So when this is true, this should be false. When this is true, this should be true. Now the way I want to do that is to flip it. If this is true, this is false. If this is false, this should be false. Does that help me? A implies, let me write this down this way. A implies B is the same thing as not A or B. So A implies B or implies not VR. So I need a not of that as a part of the confusion. And VR. Okay. And then finally, we want the and. Oh wait, no, I can't quite go that far yet. I have to go, rule 1 is going to be that or implies NVR, and there we go. rule 2. So not this or not this, and this or this. So what this means is that if it or is true, so if and or and not. So what that and means if they are equal, right? And not means if they are equal, right? To one of these, if this or this is the same as saying if they are equal. Now, if we want to say, well, I could make this a little simpler on myself, I think, right? I could compute XOR 1 and XOR 2. And this would be like, okay, so this and this, right? So if XOR if they are opposites of each other, one of these will be, hold on, let me think. One of these will be true, right? If these are opposites of each other, then one of these will be true. So if they're opposites of each other, this will be true. Then I'm going to need the not of that. So rule 1 is that if either they are opposites of each other or, right, that, and then or that. So when XOR is true, that is when they are opposites of each other, then this will be false. And so in order for this OR to come out as a true OR, this would have to be true. So when XOR is true, VR will have to be true. And when NXOR is true, NVR will have to be true. So if I AND those together into the root, I should get an XOR, right? Probably would be good once I've got a little farther along to have higher level Boolean logic helpers besides just the lowest level AND, not, and OR that I have. That's fine. Okay. So that gives me a new set of constraints. And let's turn off the solver for a moment and just make sure that it prints out in a way that looks right. I realize now that I took a risk there that this would become a giant CNF formula, but it looks like it didn't, which is kind of nice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm not sure if that makes sense, but that's what it came out as. This is pretty gnarly looking, though. Does this make sense? It doesn't really make sense to me. Let me look at this more carefully. So let's look at the formula that I came up with. You know what? Let's just give up on XOR is too complicated for me to visualize. I don't know why I went that direction. Let's do it this way instead. The goal is to implement AND across 3 bits.
so x0 and x3 that should be a not of the and. So this is saying either x0, it's not true that x0 and x3 are both true, or it is true that x6 is true. So if x0 and x3 are both true, then this is true, which makes this false, which means this will have to be true by setting x6 to true. So if I make these two true, this is true. Now if I have x0 is false and x3 is true, this comes out false, this comes out true, so x6 is free. But since x0 is false here, this comes out false, and x6 has to come out false. So that looks correct to me now. Now the formula it comes up with in the CNF land is this. What is this saying? Not x0 or not x3 or x6. x0 or not x6 and x3 or not x6. Yep. Or not x1 or not x4 or not x7 or x1 and not x7 or x4 and not x7 x1 or not x7 and x4 or not x7 or not x2, not x5, not and x8 or no, then and x2 or not x8 and x5 and not x8. Yeah, okay. All right, so that looks correct to me. And now, let's see if it can find the solution. The solution is, well, there are several solutions. I could make it just one step more interesting by finally saying that we want something like at least one of these should be true, so don't give me the all falses, or at least one of these should be false, and at least one of these should be true, so this would be like that, not. And the reason I'm doing this is to give it reasons to not just succeed by guessing everything true. Since it's set up to just guess everything true, it like wouldn't be very interesting if it succeeded. In this case, I want to see it have to crunch through problems where guessing everything true leads to something having to be false, and it having to work its way through that. So the rule I want here is like this. Rule 1. Let's start rule 1 off as a nil.
Same thing with rule 2. These are going to accumulate a few ores in them. Rule 1 equals FatSatCon or Scratch Arena Builder Rule 1 or VR1, 2 and 3. So there's rule 1. One of those has to be true. And here's rule 2. One of them has to be false. Now there's still a couple ways for it to solve it. But ooh, did I turn the solver on? I did. Okay, that was a mistake. Run. Okay, the formula still ends up pretty simple. All that should have done is it added 2 extra ores, this ore and this ore, which should translate very simply into the CNF, which it does. So now what I want to do is I want to say, what happens when we're trying to solve the formula that leads to nothing coming out? Let's let's pop open Remedy and see what that was about. The translation works just fine, but the solver appears to struggle. Why is that? All right, it should get to the end of propagation here. Oh, that's the problem. I see it now. So I don't have an incrementer here, and that's on purpose because sometimes I reset the iteration right here. So what I want to do is, if I don't reset it, then I should increment it. Let's try that. So I should be able to get to the end of propagation. There, we did. And the path that it chose should be undetermined. Good. So that should lead us to the guess state, which it does. And it's going to guess that variable 0 has value 1, because we didn't put in any kind of fancy heuristic. It just takes the first available guess. So we assign the guess. And we go back and propagate. And that guess, that variable 1 is true. I am guessing that this will lead to no additional constraint yet. Yep, so that's still undetermined. Makes another guess. Now here, I think we'll find that a propagation occurs. So we'll determine a deduction, is my guess. We didn't determine a deduction. So does that mean the path is still undetermined? Unassigned count equals 1. Double check here. X0, oh yeah, X0 and X1 don't, X0 and X1 don't relate to each other. It's X0 and X3 that I was thinking of. So we guessed this true, we guessed this true, we're gonna guess this true. And none of that will lead to any deductions, but when we guess this true, it'll lead to a deduction. Okay, got it. Whoa, what's just happened? How did we get to the end? No way we got to a sat already. Unless I just skipped over it by killing my breakpoints somehow. Let's put breakpoints on each of these so we don't miss them too easily. Okay, we're propagating, we guess. Propagate, we guess. Here, I believe we should be seeing another guess, right? The path is undetermined. And we guess variable 2. We guess variable 2 is true. We increment the guess number. Come up here, we propagate, we guess. Now we're going to guess variable 3. Yep, is true. And here we're finally going to get the fun. So the first clause, we're going to hit this once, and then we're done. So the total value is 0, but the unassigned count is 1, meaning we can now create a deduction that variable 6 is true and restart the propagation. Now, when that finishes, we should be back to undetermined, and we are. So we guess. And here we're going to guess variable, well, we've guessed 1, 2, and 3, so we'll guess variable 4, I think. We'll make that true. And that will lead to some deductions. And then that leads to SAT. All the deductions led to SAT. Okay, so that's cool. Why don't we, I think I'm close to done for today. It looks like it's working. I want to add in logging again. So I had logging before. I want to add in just a little bit of logging here. Variable equals value equals 1, t, otherwise f. Okay, so there's our deduction steps. I'm going to put the guess number on all of these as well. Tam Weil asks, how do you learn how to create a SAT solver? That's a great question. You know, I've been streaming this project since about a month ago. And so if you want to see how I've done it, it's literally all over here. If you go to Mr. Fourth Dimension on YouTube, you can just look at my videos, and there's like SAT solver from last week. There's code reading session. If you go back a little bit farther, there's code reading session for mini SATs part 1 and 2. And there's code reading CDCL SAT solver part 1 and 2. So that is most of what I've done. I did a little bit of reading outside of that, but a lot of that was just that. So I just read other people's SAT solvers, and it helps that I knew a little bit about what the SAT problem was going into it. So if you don't already know that, it won't do you any good. But if you already know about SAT and what a SAT solver is supposed to do, I read some other people's SAT solvers, got them to build and walked through them on my own, and then I watched I think one video on YouTube. There was about a 20-minute video. Let me see if I can find that one for you. Yes, this video here. So, A Peek Inside SAT Solvers by John Smock. This was a great, helpful video, 30 minutes long. And then I drew some pictures, and that's about how far I've gone in educating myself about how SAT solvers work. And the rest of it's just by writing the code and trying it out and learning as I go. Okay, so here's the deduction part, here's the guess part. Let's log the guess. CDCL is clause or conflict-driven clause learning. So it kind of builds on top of DPLL. The idea in conflict-driven clause learning is that when when you're doing a SAT solver, what you usually are doing is sort of you make some guesses, you make some deductions. The very simplest thing, you don't even have to do that. You try out a bunch of assignments to your variables until one of them works. That's the most brute force you can do. Then you can do deductions where you say, okay, given the assignments I've already made, are there any variables that I am forced to make certain deductions for those variables to be certain values? And then the idea of CDCL is normally when you find a conflict in DPLL, you would backtrack and then try a different path. Well, in CDCL, what you do is before you backtrack, you look at the conflict and you actually construct a new clause that you add to the problem. And the new clause captures the primary idea of what mistake you made. It basically says, here are constraints that are true about the problem that you didn't know about because they weren't written in the original problem. But once you add them to the problem, it guides the heuristic and it guides the deduction engine more rapidly to the solution. So it kind of remembers mistakes have been made in the process of guessing and making deductions off of those guesses. It remembers those mistakes as a clause to add to the problem, which is a pretty neat idea. That video I just showed you, the look inside SAT solvers, explains the idea pretty well. CDCL guess. Okay, so we have CDCL deduction. Let's call that deduce, guess. That's 5 letters. That's 1, 2, 3, 4, 5, 6. So we want to add an extra space there to make them all line up. And then I'm going to do a little bit heavier of a log right here. If backtrack, so that's just to tell us that we backtracked to a previous guess number. Do I plan to extend it to SMT? I don't know. That would be quite a bit more than what I've looked into so far. I know very little about that part of the constraint solver stuff. This is really my first big steps into it, is just building the SAT solver. So my hope for now is to get this up and running well enough to use it to design custom Sudoku boards or something fun like that. Package it up into a little library so that other people who want an easy to use SAT solver can play with it. If it doesn't turn out to have any real world use outside of being fun to play with, I would be okay with that. But I suspect that from there, other people who are smart can look at this and uh, it, people like in my programming circles and stuff will be able to see the interesting parts of this and take it farther. And if that happens, then I'll keep going in this direction. But I kind of am thinking if the stat solver comes out and not that many people have fun playing with it, then like I don't really have any plans. Like I'm not that big on trying to go like all in on doing constraint solving as my thing or anything. This is more just for fun. So unless other people are having fun with it, I will drop it. But if it turns out well, and especially if it seems like people are into it, then yeah, I'd be down to like learn some SMT stuff as well. For people who are listening who don't know about SMT, the idea is that a SAT solver is essentially this generic constraint solver for Boolean logic, but it can't for Sudoku I have to do all this work to encode. This is an example. Sudoku is not the only case, but for more interesting problems where you have like, oh, I want to run, like I want to look at the logic of like arithmetic, numbers that are greater than or less than or equal to each other as a part of my, I want to use expressions like instead of saying, x1 or x2 and not x1 or not x2 or not x3, right? Like you've got like, instead of just this, you start going, well, I want to say if x is greater than y and or like x is greater than y and what would you have here? X is greater than y, or x is equal to 0, and x is not equal to 0, or not, my Boolean or whatever, right? You want to start mixing in more interesting logic. That's what SMT is for. Gotcha. Yeah, I don't have that much experience on either end. Like I don't use them a whole lot. I've only played with them a little bit. I haven't written solvers for them before. It's just fun for fun. Like I'm just doing this because I think it's a neat kind of thing. They feel kind of like magic. Being able to program something by kind of just throwing problems at it and it comes back with solutions feels fun. Like it feels like fun when the computer does something a little bit magic, a little bit harder than what I normally make it do. So I just thought it'd be fun to learn how to program it to do stuff like that. It's also like it's very easy to just get stuck in the pattern of like constantly implementing the same stuff over and over again. It's like, let's make another game, let's do the graphic system, let's manage all of our files and parse our asset metadata and blah 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 blah. So sometimes it's fun to just like sit down and be like, I'm gonna do a thing that like runs a cool algorithm that solves a cool problem and figure out how to play with that to have fun with it. All right, so for this one, I'm going to make it a little bit more complicated because I want it to print out the newly learned clause while we're logging. So it's going to print like no, that's not right. So we look at our clause, it's got a literal count. We look at each literal and print it like this.
all the literals. Yeah. Sat solvers and more general constraint solvers get used to do all kinds of cool problem solving stuff. And I spend so much time doing the low level programming on stuff, but I feel like it's really important to also spend some time looking at like some of the valuable use cases of a computer rather than just constantly churning out the systems like that you know that build up computers. You got to look at the other end and be like, well, what do we actually want computers to be doing for people? Like what is the kinds of stuff we know how to solve with them that isn't just doing more computer stuff with them, but to like get something hard done. I don't know. All right, so if it's, okay, we want to print it like this, x %u variable, and this is not, and this is if I is greater than 0, you do it this way. But we could just do it this way. This would solve the problem nicely. All right, so here's my log. It guesses x0, x1, x2, x3. It deduces x6. It guesses x4, deduces 7, 8, 5. 0, 1, 2, 3, 4, 5, 6, 7, 8. And yep, it gives me a result, and that worked. Okay, cool. So it worked to find a solution here. It didn't have to do any conflict resolution. So it didn't learn a clause. So let's try one last thing. I said I would be done, but I want to just up the difficulty a little bit now. So we know it can work on very simple stuff. Let's take the Sudoku constraints, and we'll do those ones, but we'll turn down the difficulty by making it like a degree 2 instead of a degree 3. So instead of a 9 by 9, right? We'll say that this is called the n, and right now the n is 3, so the n squared is 9, and so just like everywhere where we see a 9, we're talking about an n squared. Everywhere where we see a 3, we're talking about an n. All right, and let's turn this down to a 2 and see if it can handle that. Okay, this doesn't look great. It looks like it ended before it should have, or something. And it also seems to be in a strange state that I don't think looks correct. CDCL guess. Okay, hold on. There shouldn't be any guesses at level 0. Okay, yeah, so I'm just printing that at the wrong step along the way. Guess. Let's put you after the assign instead of before. Deduce. Let's
put you after the assign. Assigned clause count. Are there any other spots where we do an assign? Yeah, you should be a deduce as well. Okay. Guesses x0 is true. Deduces x1, x2, and x3 are false. That's good. Those are all the variables relating to the first cell. x4, x8, x12. Those are all the variables relating to the first row's 1 values. 16, 32, 48. Those are all the variables relating to the first column's 1 values. 20, 20, 20. What is 20? Oh, that is the other one in this box. How is it deducing x24 is true? Let's see here. So we have a Sudoku board, which looks like this. 1, 2, 3, 4. Two, 3, 4. Okay. And just to help me visually keep it all straight, I will go through and let's replace these with these, these. No, none of those are good options. Okay, well that's fine. That's a good start. So it comes in here and it says set this to 1. Which it does. Oh, do you know what I could do? I could... Okay, this will help. This will help. So I'm going to have to make the deductions. Okay. Here's what I'm going to do. I'm going to change the way we print those to this. When we see the assign function has been called, we're going to log it. If the deduction clause is 0, then it's a guess. Variable value guess number. Otherwise, and this will all be if log is in gathering, yeah. Otherwise, it's a deduction. But before we say that's it, let's do the same thing we did here where we print out a clause. So what we might have to do is say we want something like fatsat CDCL log clause, and that just means we have to put a clause in there, and then we can emit a new line manually at the end. And so then this would become, you do this, this, oops, do this. This here's how you do it. And we replace that with emit a clause, learned clause. So learned clause just becomes a clause now. And this just goes and lives as the implementation for this.
Okay. Guess the x0 is true. And now it's telling us why it's making certain deductions, right? So it'll go, oh, I deduced that x1 was true because of this clause. x0 is false and x1 is false. And that makes sense because we have x0 is true, right? So now we can see all of these deductions that I said made sense. We can see the clause for them. What is this one, though? x4, x8, x20, and x24. Who is that? Why is there a clause like that? x4, x8, x12, x16, x20, this is a little confusing. I'm not sure that I am convinced the variables are laid out correctly. So let's use this to mark down the names of the variables that should appear in each of these. So 0, 1, 2, 3. I believe the way it should work is this should be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. See how far this gets us. Okay. E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. Okay, so not quite the whole board, a little over half, right? So it's saying 24 got deduced to true. 24 is O. O should be right here. Yeah, that seems like total nonsense, right? So x0, 1, 2, and 3, right? So this gets set to true. That forces these to false. That makes sense. That forces this, and this. C is 12. This, and this to false. That makes sense. 16. 32. Yeah, that makes sense. 48, we didn't get that far, but if we kept going, 40, 41, 42, 43, 44, 45, 46, 47, 48. It would look like this. 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Very good. Z, so then AB, CD, EF, GH, IJ, KL, MN, OP. Okay, so M is little 48 is, yes, that's in the right spot. Now, where is 20? 20 is K. Right there.
That makes sense because that is inside the same box as this. So when we set that this should be the number 1, this should not be the number 1, right? So this would be, K would be true if there was a 1 in this box, but 0 is true if there's a 1 in this box. So these shouldn't go together. That makes sense. So then O became 24. And that got set to true. I don't feel like I buy that that should be getting set to true. What is this constraint here? It's saying one of these must be true. 4, which is this one. 8, which is this one. 20, which is this one. And 24, which is this one. Yeah, that's garbage. That constraint's just wrong. So our constraints aren't coming out correctly, which might be why it doesn't work. Let's take a look. So that looks like it's coming from the box constraints, probably. So we are looping over we're looking at each box. There are 4 of them. We're looking at each number. There are 4 of them. Four times. So X comes from, what is K? K is going 1, 2, 3, 4, and we're going 0, 1, 2, 0, 1, 0, 1. This should be going 0, 0, 1, 1. So the cell index is the X value, which is the box X. That's wrong. Look at that. So box X is going 1, 2, 3, 4. And so this is going 0, 1, 0, 1. But then we're taking box X as this needs to be times by N. I think it'd just be easier to do it up here. And I know this looks funny, divides by n and then multiplies by n. Can that be right? Well, yes, we're relying on the rounding here. So this is going 0, 1, 2, 3, then we're dividing it by 2, so it's going 0, 0, 1, 1, then we're multiplying it by 2, so it's going 0, 0, 2, 2. Let's see how that goes. All right, it still stopped without saying that it succeeded, which seems fishy, but it does look like it got into a much better rhythm here. Okay. 0, 1, 2, 3, 4, 8, 12, 16, 32, 48, and 20. Good. Then it made a guess, and it decided to guess 5. So it put a 1 here, now it's putting a 2 here. Great. And that leads to zeroing out this and this, this and this. 21. L. 21 is L, is right here. Yes, because we said that's a 2, so that should not be a 2. Little b should not be a 2, which is 37. And we got to go a little farther. M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. 49. Well, hold on. Okay, so P, Q, R, S, T. So there we go. So that cancels out L, little b, and R, turns out, which is good. And it cancels out 17. 17 is H. Yeah, that makes sense. So that got wiped out because it's in the same box as that. And then it made a guess for X10. That's this one. So we'll put a 1 here, a 2 here, and a 3 here. 18. That's I. A 1 here, a 2 here, a 3 here. Why didn't it go to 15? Oh, it did. Ah, right. It found 15 during a deduction. So this and this were guesses, and then it's deducing 15 is true right here. Cool. Then its next guess is 18. That's I. So it's saying, okay, we got a 1 and a 2 in this box, so 3 is the next available thing in order. That forces a deduction here on 23, which is N. Yep, makes sense. To fill in that box. And it also spills out all of this stuff here. Guess is 24. That's O. So that means I put a 1 here. So it's got a 1, 2, 3, 4. A 3, 4, 1. I'll count something here. 1, 2, 3, 4, 5, 6, 7 guesses plus 1, 2, 3, 4, 5, 6, 7, 8, 9. 7 plus 9 would be 16. How many trues did it assign? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it looks like it might have finished the problem, actually. So why didn't it say so at the end? That's a little confusing. It should have gotten to the end and said, hey, we found a result sat by blah. But it looks like it didn't do that. And I'm not sure why. Oh, you know what probably happened is probably because I manually print the log again, and so it did do that, and I'm just reading past the end where it logged it again. There it is. Okay, result sat. So it was cool. It can solve the the rank 2 Sudoku. Let's see if it can do that on the rank 3 Sudoku. So let's delete the old one because that one probably has a bug, the same bug that we found in when we were fixing the small ones. Just change the rank to 3, run it, and hopefully, hey, it finishes. Okay, cool. So I think result sat by and then blah, blah, blah. Great. It took it 45 guesses, but it did it. It solved it built a Sudoku board. So I can't see the Sudoku board because instead of giving me a Sudoku board, what it gives me is a bunch of assignments of variables, where these variables have a sort of projectional relationship back to the Sudoku board, right? They have a one-to-one correspondence, satisfying assignments of the variables and correct Sudoku boards correlate to one another, but I don't have anything to do the conversion back.
to the Sudoku visualization. We could do that if we wanted. We could scan through this and print out a Sudoku board. Want to see? Want to see that? I kind of want to see that. So let's come in here. Let's turn off the log. So to turn off the log, all I have to do is say, do not begin accumulation. And then it's only going to print that final result, not the thing, right? Let's also just say we don't want we don't even want this part anymore. But in fact, why don't we just do this as log emit from now on? Right, so that won't come out for now because we've turned off the log. But let's say there's an easier way to turn off the log, I think. Let's do it this way. It's fine for now. Seems like it's running pretty fast. So that's good. What I want to see is what happens if print Sudoku solution. Okay, so for this, what I have to do is we want to do a loop over each row. How is it not finding the rank? Ah, that's why. For each row, for each column, then we want to figure out the number. So this will start by saying, give me the cell index. That is computed this way. The column tells us the X value, the row tells us the Y value. And then we want to say, give me the correct number. So we'll start by setting the number to 0, and it should become a 1 or a 9. So somewhere between 1 and 9, since we have a solution, right? And so what we'll do is we'll scan equals 0 to n2. And we're looking at the solution. So let's go look at fatsat.h. What does the solution look like? So the solution is made up of values and if one of those is true, then we set num equal to I plus 1 and break. So there's our number. It's whichever one, but it's not I. It's got to be cell index plus I, right? So cell index tells us what cell we're on, and then we scan through the 9 separate booleans that tell us which different numbers can go into that cell. If one of those is true, that is what we want to print, and so we then go num, and then after a row, we'll put down a new line. Right? And then let's skip logging the constraints in the CNF. Oh boy, there it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. 1, 2, 3. 7, 8, 9. 1, 2, 3, 4, 5, 6. 2, 1, 4, 3, 6, 5, 8, 9, 7. 3, 6, 5, 8, 9, 7, 2, 1, 4. Oh man. 8, 9, 7, 2, 1, 4, 3, 6, 5. Yeah. Yeah, these all look correct. That's it. So that's just generating from a blank board. So where does that leave me on this project? So I have a Sudoku solver built on a SAT solver, but I don't have the ability to put in constraints on the Sudoku board yet. So let's go and look at my to-do list. Where's my to-do list? So we have the faster analysis algorithm now. But the rest of these I still need to do in additional passes. So these would help to speed it up more. As you've seen, it's already pretty fast. But if I start putting in fancier constraints that I don't have right now, it could get slow again. Just putting in numbers into the grid wouldn't be a problem. But if I want to do some like, you know, of the more wild, you know, Sudoku stuff that isn't just numbers on a grid, but additional rules, that'll get interesting. I want to be able to do features like assigning variables, fixing variable assignments before solve. So now I've got the Sudoku constraints built, and I've got the solver. I'd like to be able to assign some variables to be like, here are some numbers that I already know. I'd like to be able to have higher level constraint writing APIs. What else? I don't know. That might be a good set of new to-dos to add based on where we're at. Yeah, okay. I think that's a good spot for now. That'll be it for the stream today. Yeah, this was a good one. We actually got to write a whole SAT solver from scratch. I guess one other thing I'll do is I'll clean up the the blocked out code from the old one that I didn't keep. Yeah, that one we eliminated. This one we eliminated. That other one was super buggy, so the fact that we got to it working correctly today and running really fast on Sudoku is really cool. I think that's awesome. I don't think, if I go back, that I don't think we've actually finished testing. And the reason I say that is if we look at the log of this running, I don't think it learns anything. Oh, it does. Look at this. Okay, so the learning process is actually a part of this too. It made a mistake. How many times did it have to learn? Once, twice, 3, 4, 5, 6, 7, 8, 9, 10. Okay, cool. So right around here, it had to, out of how many guesses did it make total to get there? 45. So there are 45 free decisions it had to make to choose a board. And there's this one spot where it got itself stuck and it had to keep backtracking and guessing something different. So like, what do the clauses look like that it learned? So these big monster clauses: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 15 for that first one that it learned. Looks like it learned a bunch of really big clauses. Which I guess is not that surprising because we have a few clauses in there that are like 9 variables, 9 literals. And so if it hits even one of them, it blows up and then it hits a couple other clauses or hits 2 of those or something, and then you just get these giant things that it learned. But on the other hand, can we see, so here's the guess it made, x118 equals true. It ran some deductions. This is where I think another great next step might be to visualizer, so we could look at this happening visually. It would be a really neat thing to have. So it makes a guess. It runs these deductions, and then it has to backtrack. Now, when it says it has to backtrack, we don't know necessarily why. We can't see that in the log. Maybe I could add a thing that prints out the conflict clause that it hit initially. But it should include in there, yeah, that it needs to not set x118. So while all of these things were there, it must not set that to true. So then it deduces x118 false, and it guesses x119. So there's a couple interpretations here. One is that it's just, this is where it had a lot of constraints on this particular square. And so it probably is going to come over here and learn that x119 can't be true. Yeah. Man, it learned that before it learned anything else. I put that right in there. But anyways, it deduces that that should be false. Guesses x123, backtracks to 12. x123 is false. So it deduces x123 is false. It makes some further deductions on level 12. And then it backtracks again. So when we look at 12, the guess on 12, it's x108. So it should be on this one learning that x108 needs to be false, which it does. And so then it guesses x109, and it's got all these learned clauses there. That is so cool. Here, x109 becomes false. So yeah, it has to try again a couple times at this level to find a combination that works. But we can't really see visually what it's trying again a couple times, which is a shame. I think it'd be fun to be able to see that. But it looks like, yeah, it looks like there was just one spot somewhere in the middle there where it kind of backed itself into a corner and had to backtrack a couple times, and then it made forward progress for the rest of it without an issue. So that seems like a good place to stop for me. Thanks for coming to hang out if you did. If you're here, I'd like to let you know that tomorrow I'll be streaming probably around noon Pacific time, so about an hour earlier than now. It could be closer to, it could be later than that, it could be a little sooner than that. But somewhere between noon, so an hour ago today, to now, I'll start a stream, but it won't be on this channel. I'm going to be streaming with Abner Coimbray, so you can check that out tomorrow. We'll be talking about his project and how he's using some of my code in his project, so I'm going to go hang out and give him some advice on how I use my code, so hopefully that'll help him. And then I'll be back on this project next Friday, probably. On Mondays, I stream my other big project, the story engine, and then on Fridays I do whatever I feel is fun, which lately has been the stat solver.
if you're interested in this project or any of the projects I have going on, make sure you go over to mrforth.com and sign up for news. I post my news once every month or two, so you can follow along there. You can also go over to software and check out some of the stuff that's already out and open, like the code base that I use and stuff. It's all out there. You can go and find and use a lot of the code that you see here, and stuff like FATSAT will probably come out on the same website sooner or later. So yeah, thanks for coming to hang out, and I'll see you all around the internet. Bye.